Assalamualaikum everyone. In today's lesson, we would be covering the A-level May June 2020 paper 1 2. This will be the part 1, so I would only be covering from question number 1 to question number 10 with detailed explanations. So you will get to see 3 more videos on this single paper. So let's begin. The first question states, in which carbon allotrope are all electrons localized? Now, for this question, you really need to imagine what each of the allotrope of carbon looks like. And here's a rough sketch that I have made for all of you. So this right here is graphite, and this right here is diamond, and this right here is Buckminster fullerene. Now, what graphene basically is it's this. Just single layer of graphite is graphene. Now, what we have to do is we need to tell which of these allotropes has all electrons which are localized. For this, what you need to know essentially is that if I take, let's say, this carbon of graphite, you can notice that it makes one bond, two bond, and three bonds. And we know that carbon has to make four bonds. So if the carbon in graphite over here, maybe let's look at this one. So in this we have a carbon making one bond, two bond, and three bonds. So because in graphite, and same goes for graphene, if they're making three bonds, if carbon is making three bonds, the fourth electron of carbon will be what we call as delocalized. And if you look at Buckminster fullerene, you would notice a similar thing. You have a carbon, okay, you have a carbon which is making one bond, two bond, and three bonds. Alright, you can easily see this. So one bond, two bond, and the third bond, right? So because carbon is also making three bonds in Buckminster fullerene, that means that the fourth electron will be delocalized. However, when we look at diamond, we know that it has a tetrahedral structure in which each carbon is bonded to four other carbon atoms in this way. And because it is bonded with four other carbon atoms, the fourth electron is not delocalized. And if it's not delocalized, essentially it will be localized. And therefore, the answer is B. Question number 2. Copper ore contains 3% of copper carbonate by mass. Which mass of copper would be obtained from 1 ton of the ore? Now, in order to solve this question, make a mind map in your head. Here's one. So we have the ore, alright? So technically you have the mass of the ore, alright? From the mass of the ore, we can get to the mass of copper carbonate because we know it's 3%. And from there, we can get to the mass of copper. So here's how you will basically solve it. So the mass of the ore is 1 ton, right? And you can also write this down as 1000 kg because 1 ton is equal to 1000 kg. And the mass of copper carbonate, right? Mass of copper carbonate is going to be what? 3% of this, right? So 3% of your 1000 kg, and that basically gives you 30 kg. Now that I have mass of copper carbonate, I can easily get to the mass of copper, and that's by doing this. I know that copper has a AR of 63.5, right? How do we find the percentage composition by mass? You have the AR of that element, and then you have the MR of the molecule, which is 123.5 in this case, right? And what do? You multiply it by 100, and what do you get? You get, you basically get the percentage composition by mass. Now, right now, I specifically want to know this fraction in 30 kg. So I will multiply it by 30, right? And that gives off 15.4 kg. So there you go. The answer is C. Question number 3. The catalyzed formation of ammonia by the Haber process can be represented by the equation shown. Which change in conditions will increase both the rate of formation and the equilibrium yield of ammonia? So one important thing to note over here, or something that I would like to point out, is this. This is a table. If you can memorize it, well, it's going to be fantastic, because here's the thing. The rate depends on the temperature, the concentration, the pressure, the surface area, and the catalyst, and it has a direct relationship with all of them. One thing that I would like to point out, the pressure is only effective when we have mainly gases involved in a reaction. Okay, so the rate increases if you increase the temperature, if you increase the concentration, if you increase the pressure, if you increase the surface area, and if you increase the amount of catalyst, or basically use a better catalyst or a catalyst in the first place. The equilibrium, however, depends only on temperature, concentration, and pressure. And depending in which direction the equilibrium position heads depends on the conditions given. Now, if you want to increase the rate of formation of ammonia, if you want to increase the rate of the reaction, you need to do either of these, increase either of these. So let's look at the options. Decrease the temperature. That can't happen. Increase the temperature, well and good. Increase the pressure, well and good. Increase the surface area of the catalyst, well and good. However, because we also need to increase the equilibrium yield, right, and because the increase in the surface area of the catalyst has no impact on the equilibrium yield, D cannot be the answer. So it's either B or C. Now let's look at the conditions. We want to favor the forward reaction if we want more ammonia to be formed, and therefore we need to do something with the temperature which suits the forward reaction. The forward reaction is exothermic in nature. We know that because of this negative sign. And therefore, we also know that when you decrease the temperature, your exothermic reaction is favored, or it is increased. Now, because the option over here says increase in the temperature, yes, it will increase the rate, but it would definitely not increase the equilibrium yield of ammonia, because increase in temperature will favor the reaction which is endothermic in nature, in this case, the reverse reaction. So B can't be the answer. The answer is C. And that makes sense because you have 4 moles here, 2 moles here. Increasing the pressure always favors the side with less gaseous moles. So that's ammonia. Question number 4. So this question is basically about the standard enthalpy of atomization of sulfur. Well, I can ignore sulfur for now. What I need you to understand is this general form. Now, in this general form, here are a few things that you should note. And if you make sure that all of these are fulfilled each time that you write your equation for the standard enthalpy of atomization, you would never go wrong. So the first thing is that right over here, you would always write the standard state of that element, all right, at RTP. So at RTP, whatever the standard state is, it must go over here. This right here should always be the formula representing that molecule in its standard state. So formula at RTP, again, the standard state, because for us, the standard is the conditions which suit RTP, that is 25 degrees Celsius or 298 Kelvin and 180 M. So make sure that this formula is of that molecule when it is at RTP. Another thing that you need to make sure is that this should always be 1 mole. So the product must always be 1 mole, and this is very important to remember. Now, the fourth thing is making sure that this right here, this state, the product state, is always a gas. The product state must always be a gas. Okay, because it's in atomization, we basically make it in its gaseous form. And this right here, right, should always be an atom. So no matter if something exists as a molecule or whatever, but X always needs to be an atom. And last but not least, right over here, we will add some sort of a coefficient that will balance off this 1 mole. Now let's see an example. In this case, we're talking about sulfur. And we know that sulfur, the formula of sulfur at RTP is S8. And the standard state at RTP for sulfur is solid. Now this is something that you should know by now. It's something that you've already done in O levels, that sulfur at RTP is a yellow solid. So you must know that. And what we want to form is an atom. So I just require a sulfur atom, and it should always be 1 mole. Now let's balance this off. If I want to balance this, I have 8 sulfurs here, 1 sulfur here. What do? I add 1 over 8 over here. And the last thing that I do is I add the gaseous sign here. Let's see which complements that. So 1 over 8, S8, solid, 1S, gas. So there you go. That's your answer. The problem with the option B is that this right here is a gas, whereas it should be the standard state at RTP. This right here balances it in the wrong way, because this should always be 1 mole. Okay, moving on. Question number 5. Okay, so in this case, you should use changes in oxidation numbers, right, to balance a chemical equation. And so what they're saying is give us this CD ratio. So whenever you have a redox reaction in which you see a lot of electrons being exchanged, the first thing that you do is you write down the oxidation states. So because oxygen is -2 and we have 2 oxygen here, -4 that would be, and to make the overall charge 0, manganese must be +4. If you don't know this, you need to revise this. I might make a video on this as well, but for now I'm assuming you can do at least this bit. Now, manganese over here is 2 plus, and over here it would be, well, oxygen is -2, 4 of them makes it -8. The overall charge on the molecule is -1, so manganese would have a charge of +7. Now, I see that manganese goes from +4 to +7. What that means is a loss of 3 electrons, and I see manganese go from +4 to +2, which is a gain of 2 electrons. If I write these separately over here, what I see is Mn going from +4 to Mn +7, and in this case I see a loss of 3 electrons. I also see manganese going from +4 to +2. It's actually 2 plus, but as I'm writing the oxidation states, this is actually the preferred way. And this is 2 electrons being added. To balance it off, right, to balance the number of electrons lost and gained, I add 2 here and 3 here, so that 6 electrons are lost and 6 electrons are gained. And I would simply use these coefficients and plug them here. So what I see is I need 2 and 3, 5 Mn4 plus, so A becomes 5, and I require 2 Mn7 plus, so this right here becomes 2, and I require 3 Mn2 plus, so this right here becomes 3, and our question is more or less solved because they say what is the ratio of C to D, and C to D we see that the ratio is 3:2, so the answer is D. However, I'll still go on and find B and E as well. Now you can clearly see that we have how many? 10 oxygens on this side, and over here we have, well, 8 oxygens. So E should be 2, so that I have 10 oxygens on this side as well. Now this makes it 4 hydrogen here, so to balance the hydrogen off, I add 4 here. I hope that makes sense. Moving on. Question number 6, right? So air contains, we need to assume that it contains 21% of oxygen, and it says what is the minimum volume of air required for the combustion of 10 cubic centimeter of butane. So here is the balanced equation for this reaction. What we get to see is that there's butane and oxygen and carbon dioxide and H2O. I've used it in this form. I've balanced it off and kept oxygen in its fraction coefficient. Now, here's the thing. They said that butane gas, and that's something you should know. The first 4 alkanes are gases. So the state over here for butane is gas, oxygen is a gas, carbon dioxide is a gas, and you must know that when combustion happens, there's a lot of heat that is released, and because of that heat, your water is in fact in the form of steam. I hope you know that, but I still clarified it here. This is important because when you have gases, when on the reactant side, on the product side, when all of them are gases, we can use what we call as the Gay-Lussac's law. And what that states is that when you have a reaction that involves purely gases, then the gaseous reactants to the gaseous products, basically the coefficients or the molar ratios can be simplified or are simple whole number ratios. And that's what you can exactly see here. If I double this up, it will become a simple whole number ratio. However, here's what I will do. One of the, you could say, the derivatives of Gay-Lussac's law is the fact that when in a chemical reaction, your reactants and your products, all of them are gases, you can actually treat these molar ratios as the ratios of volume as well. What I mean by that is, here's the thing. Here's how I'll simplify this question. If butane is 10 cubic centimeter and I use this molar ratio as the volume ratio as well, then I simply have to multiply 13 over 2, which is 6.5, by 10, because here's the thing. You have your butane, that is 1 mole, and oxygen is 13 over 2 moles. If I'm treating their molar ratios as their volume ratios and I cross multiply, I get my oxygen as 65 cubic centimeter. So my oxygen is 65 cubic centimeter. Now this is how I simplified my question. If you do it with the mole method, you will still be able to solve it, treating it as that at RTP a gas occupies 24 cubic dm cube. But to simplify this question, I've actually used the derivative that we get through the Gay-Lussac's law. Now here's the thing. I have the volume of oxygen required, but what did they ask for? They asked for the minimum volume of air. So what I will do is I'll say, well, let's assume that the volume of air is X, all right? And I know that 21% of that, okay, is equal to what I got just right here, which is 65, right? So I've some volume of air, and because oxygen is only 21% of that, it would be equal to 65. That's what was present here. So when you solve this, right, when you solve this question, you should end up with 309.5, which is about 310 cubic centimeters, sorry. So the answer is D. Let's move on. So question number 7, we have a aqueous bromine, okay, and then we have cyclohexane, and they're allowed to stand, and 2 layers are formed. The top cyclohexane layer is colored, and the bottom layer is and the aqueous, that's the aqueous layer, is almost colorless. So let's say this is a bottle of bromine. Bromine has a orange yellow color when it is in aqueous form. So what actually happens in this case is, here's the thing. Let me make a partition, all right? So let's say over here I have my cyclohexane. Now note that cyclohexane is an alkane, okay? This is a alkane. It's not an alkene, so I won't be expecting it to make aqueous bromine colorless, all right, or something of that sort. And at the same time, because it's an alkane, it won't really react with aqueous bromine, all right. There is a reaction, there's a free radical substitution reaction, but there's no mention of light or UV light here, so I will ignore that. So this is cyclohexane right here, and over here we have water. Now here's what you need to realize. Water is polar in nature, all right? It's polar, and cyclohexane alkane is non-polar, right? So what about bromine, right? Bromine itself is what? Non-polar. So initially bromine was in water, but when you provide it with a medium in which it had more attraction for, because we know like dissolves like, bromine was more attracted towards cyclohexane, which is non-polar. It wanted to dissolve more in cyclohexane than in water. So this bromine is actually going to shift into the cyclohexane layer. Initially, one thing to note here is that your cyclohexane is actually colorless, right? It's colorless. But when you add it, why does it become colored? Because bromine will actually shift from water to the alkane, and because water itself is colorless, the color this color that was present was because of bromine. Now that it has shifted to cyclohexane, the bottom layer, which is water, is now going to be colorless. So the reason is just, you can say, the attraction or when a substance, how much does it prefer to dissolve in a certain substance, and the key for that is like dissolves like. So non-polar will dissolve non-polar, and therefore it says, first part says bromine is reduced to bromide ions. Nothing of that sort happens. I told you again previously that there's no chemical reaction occurring because it's an alkane. Bromine molecules are non-polar. That's the right answer. Bromine reacts with water but cannot react with cyclohexane. Remember, dissolving is a physical process. It's no chemical reaction happening over here. The product of the reaction between bromine and cyclohexane is color. So there is no reaction between bromine and your aqueous, the bromine and cyclohexane. In case of UV light and light specifically mentioned, I would have thought about the free radical substitution, but that has not been mentioned, so I'll ignore that. Moving on, question number 8. In which change are only temporary dipole-induced dipole forces overcome? So what they're talking about are van der Waals forces, right? So there should be no other forces present, no other intermolecular forces present. Looking at A, you can clearly see there's OH, and it's basically a alcohol. And because hydrogen is directly attached to oxygen, there will be hydrogen bonding in this case, so A is not the answer. The second one is water, and definitely water has hydrogen bonding, so we won't consider that. In C, we have oxygen, which, my friends, is a non-polar molecule. So therefore, the answer would be C. In the case of D, now here's the thing. In the case of D, C4H10, we do call it as a non-polar molecule. That is true. But at the same time, although the CH bond is, the dipole moment in this case is very small, because the difference in electronegativity is not that significant. So we say, CH bond is more or less a non-polar bond. But it's not exactly non-polar. It is approximately, you could say, non-polar, but not exactly non-polar. So there will be still some difference in electronegativity, and so a small amount of dipole will be present. So the answer for this would be C. That is oxygen, because oxygen it looks something like this. There are two you have two atoms with similar with the same electronegativities, so there will be no chance for a dipole moment. There will be a temporary one, but not a permanent one. So the answer is C. Okay, question number 9. The complete combustion of 2 moles of alkane. So we have 2 moles of an alkane. It produces 400 m³ of carbon dioxide, and you have 301, the temperature and the pressure. So what I have been given is basically the volume of CO2, which is 400 m³, and I have been given the temperature, which is 301 Kelvin, and I have been given the pressure 1 × 10⁵ 5 pascals. But the moles I have been given for this alkane, which is 2. Okay, so they're saying, what is the formula of this alkane? So what hits, the first thought that comes into my head is, how about I find the moles of CO2? And how do I do that? Because they say it behaves as an ideal gas. That's a hint towards the general gas equation, which is PV is equal to nRT. In order to find N, I would do PV over RT. And now we need to plug in the values. So being careful about the units. Pressure is 1 × 10⁵, well and good. Volume, make sure it's in cubic meters. So it's because it's in dm³, and to convert it into cubic meters, I need to divide it by 1000 or multiply it by 10⁻⁻3. The general gas constant is 8.31, and the temperature, which needs to be in Kelvin, already is 301. And what I get in this case is 15.99 moles, which is about 16 moles for CO2. Now here's the thing. Let's say I have this alkane, and we know the general formula for alkanes is CnH2n+2. It's reacting with oxygen, and that basically gives us what? CO2 plus H2. Because it's complete combustion, we will get CO2. Now here's the thing, and here's where it's written complete combustion. Okay, so here's the thing. They said we have 2 moles of alkane, so there's 2 moles of alkane. Okay, so if there's 2 moles of alkane, then in order to balance this equation, how many carbons do I have on this side? 2n, right? So 2n. So I would write 2n over here. Now that simplifies things very quickly. I don't need to go further on. Why? Because I know this 2n is equivalent to 16. And that makes n is equal to 8. And if n is 8, I can come up with my formula. C8H18. There you go. So the answer is A. A good point to note over here is that I'll actually rub this off and write it here. A good point to note here is whenever you have an alkane which is reacting, and let's consider you are given 1 mole here, remember that you will always get NCO2 and always N+1 H2O. Remember that. It's a very good point to remember. As long as you have 1 mole here, CO2 will always be NCO2 and H2O will always be N+1. You can do that for the questions and see that it always works. Okay, now going on to question number 10. They say, in which reaction does an element undergo the largest change in oxidation number? So let's see. We have Cl as 0 here. We have Cl as if this is -2, right? So this right here is Cl generally. Well, here's the thing: if this is OCl, which one is more electronegative? Oxygen, right? So oxygen would be -2. Then what should Cl be in order for this to be minus? Overall molecule to be minus, it's that it should be +1, and then overall the charge would be negative, right? So what do we see? We see Cl going from 0 to +1, and also Cl going from 0 to -1. Let's look at part B. Cl is going from 0, so each oxygen is -2, 3 oxygens -6, overall charge should be -1, so Cl would be +5. And in this case, you can clearly see there's a very huge change in chlorine. It's going from 0 to +5. Let's look over here. So 7 oxygen -14, 2 we have to give, so this will be +6, and it's going from +6 to +3. And iron is going from +2 to +3, so not a huge change. And then let's look at manganese. So manganese, so this is going to be -8. All right, -8 minus, so this will be how much? -8 +6, so this will be +6, -2 +4, and this right here would be -8 -7 +7. So again, if I look at the oxidation numbers that I've written, the biggest change is in part B, so the answer for this would be B. Now I hope you guys found this video helpful. If you did, don't forget to give it a thumbs up, maybe leave a comment down below, and do subscribe. Until the next video, Khuda Hafiz.